Hi, everybody. Welcome to the mini lesson in mini lecture in chapter 3. In this lecture, I'm going to be covering some basic characteristics of carbon, and then I'm going to go through those two tables of functional groups and talk a little bit about just really briefly what they are and their purpose as you get further into these biological macromolecules. I will not be doing lectures on the different categories, so like the carbohydrates, lipids, proteins, nucleic acids. I think there's enough already made resources out there. You can use the PowerPoints that I made, the lecture notes, Wendy Riggs's lectures, the course, crash course, Bozeman Science. So those all have really good resources. So I didn't want to have to reinvent the wheel, just teaching things that other people have done a really good job with. But I did want to talk about functional groups and the versatility of carbon. So let's go ahead and get started. Okay, so when we start looking at carbon as being the foundation of the skeleton, if you will, of all of these organic molecules, we have to take a look back at the atomic structure of carbon. So remember, it was atomic number 6. So if here's the nucleus, it has 6 protons and 6 neutrons. And then in its valence shells, it's going to have 1 electron, 2 electrons in that first S shell. And then it's going to have 4 electrons out here. So when it has 4 electrons in its valence shell, it's kind of right in the middle of that octet. It can either get rid of 4 electrons or it can gain 4 electrons. And because it doesn't have a super high electronegativity, it's not one to go and steal electrons like chlorine or fluorine or oxygen would. So it does a really good job of sharing those electrons. And because of that, it's got 4 valence electrons, which means it has 4 to share, and it can produce up to 4 covalent bonds with other things that have electrons to share. When we look at those other atoms that are important in biological molecules are HONC, right? So hydrogen, oxygen, nitrogen, and carbon. They're calling halogens, which would be like chlorine and fluorine. Are important in some things like sodium chloride. We saw that with the ionic bonds. But with these 4 major atoms, hydrogen, oxygen, nitrogen, and carbon, we can see the number of valence electrons. Nitrogen has 5, oxygen has 6, and hydrogen has 1. And then we take a look at how many of those electrons are available to share. Nitrogen has 3 to share, oxygen has 2 to share, hydrogen has 1 to share, which is a direct correlation to how many bonds they can make. So hydrogens can only make 1 covalent bond. Oxygen can make 2 single bonds or 1 double bond. Nitrogen can make 3 single bonds, a single and a double, or 1 triple bond. And then carbon can make a wide variety. It can make 4 single bonds, it can do 2 double bonds, it can do 1 single and 1 triple. So whatever the combination is, to have 4 potential bonding capacities. So that is what makes carbon so versatile in its ability to make a wide variety of organic molecules. So when you watch those other lectures and read through the sections on carbohydrates and lipids and proteins and nucleic acids, you're going to see this diversity of organic molecules, and they all are going to have carbon at the core of their molecule. So let's take a look at some very basic carbon-based molecules. These are called hydrocarbons, and they only contain hydrogen and carbon. So some of the most basic ones would be methane, is a carbon with 4 bonds to hydrogen, each one having 1. So that's the most basic hydrocarbon you can have, is CH4. And then you can build that out. You can have 2 carbons saturated with hydrogens. This is called ethane. Then you can have 3 carbons called propane and 4 carbons called butane, and so forth and so on. They get these huge carbon molecules, but they're very simple. They can only do so much. They're nonpolar. They're hydrophobic because they have no polar charges to allow water molecules to be attracted to them. And we can even see some really huge hydrocarbons in gasoline, diesel, motor oil, and plastics. But again, they're all hydrophobic. They're all just carbon and hydrogen, and they can't really have much diversity based on They can just store a lot of energy. And so that's why gasoline, diesel, and motor oil can be used, or mainly just gas and diesel, as a chemical fuel source, because there's a whole bunch of energy stored in all of those covalent bonds between every carbon molecule. But that's about it. We don't get a lot of biological diversity for just dealing with hydrocarbons. So what we can do is we can take this variability and versatility of carbon's atomic structure and start changing things up, right? So here's those basic ones I just showed you. So the ethane, the propane, the methane would just be the single carbon with the 4 hydrogens. So they can be changed, like what we just saw in those hydrocarbons. We can throw in some double bonds. So if we put in a double bond, we might get butene, right? Or maybe we can take these long chains and wrap them around and give you ring-like structures like benzene and cyclopentane. Or we can have branches. So you have a chain and then maybe off on one side, instead of having a hydrocarbon or a hydrogen, you now have these chains. And my head's kind of covering this one. You can see it in the book. But here we have a ring and a chain coming off of that particular molecule. So I want to say the sky's the limit for all of the variability that we can have with these carbon skeletons, these carbon backbones. But again, ignoring this one here in part E with the oxygen stuck to it, everything else is just still hydrocarbons. They're limited. They're all nonpolar. They're just carbons and hydrogens. They're going to be repelled by water. They're all going to be hydrophobic. So they're limited in their capabilities. But what if we were to add some other atoms instead of hydrogens? Let's add some other atoms to those carbon backbones, and that might give us a little bit slightly different function, right? The structure and function relationships coming back as this biological theme here in organic molecules. So this is where we're going to get to these functional groups. So when we take a look at a functional group in this table, and I know my head's going to covering part of these tables, so you have this in your textbook, table 3.1. So when we talk about the R group is just what's called a remainder. It is the whatever else that this functional group is hooked onto. So if I wanted to, I could make a 3-carbon chain, and that would be my R group. And I am adding hydrogens to it, right? So let's say I start off with this propane. I think 3 is propane. Okay, so it's going to be a nonpolar hydrophobic 3-carbon chain, and that's all it is. But what if I were to remove that last hydrogen and put something else on there, like an OH group? Okay. Now, oxygen, if you remember, is high electronegativity, and when oxygen binds to carbon or hydrogen, there would be a little bond right here. I can put in there. So when oxygen binds to either carbon or hydrogen, there's going to be some unequal sharing of electrons. And so that's going to make this molecule, which originally was hydrophobic and nonpolar, now that we've hooked it all together, this whole molecule now has some polar properties to it. So hydroxyl groups, they're just an OH connected to something. In this case, I connected it to 3 carbons. Over here in the alcohols, this ethanol, this is a 2-carbon chain, removed one of the hydrogens, added this OH group, and this is ethanol. This is the alcohol that's found in alcoholic beverages. This is what your body metabolizes when you consume alcoholic beverages. It's way different than ethane, which is the nonpolar hydrophobic gas, ethane gas. When you put the hydroxyl group onto it, it completely changes the identity of that carbon skeleton. That's what these are called, functional groups. They're collections of atoms that when added to a carbon skeleton changes the characteristic of that carbon skeleton. All right, so the blue box right here, this is the hydroxyl group. It's just an OH added onto something. That's the R group. The next is called carbonyl. So a carbonyl is a double bonded carbon to a hydrogen, or sorry, to an oxygen. So here we have a carbonyl group here and a carbonyl group here. There's 2 kinds, depending on if there's a hydrogen on one end or another carbon on one end. So for example, an aldehyde right here, this is formaldehyde, the stuff that they put in embalming fluid that preserves tissues. So it is a carbon double bonded to an oxygen and 2 hydrogens on either side. So that's an aldehyde. If you have, this is called a ketone. So a ketone. So a ketone is a carbon double bonded to an oxygen with not hydrogens on one side, a carbon or some other part of a molecule. So the carbon double bonded oxygen is going to be in between, kind of in the middle of some stuff. Okay. A carboxyl group. So here's our next group. This is a C. Sometimes you'll see it as written COOH. Coo. But it's not linearly connected like that. You can't say there's going to be covalent bonds like that. It doesn't work that way. It is more accurately stated or written where you have a carbon double bonded to an oxygen, single bonded to an oxygen that is single bonded to hydrogen, kind of like what we see in these gray boxes. So carboxyls or carboxylic acids, these are they give that R group, whatever that, I could put another carbon over here and another carbon. It would give this molecule the ability to be acidic because it can release. If we release this hydrogen, we're donating hydrogen ions, which we know that is an acid. So something that can release hydrogen ions is considered an acid. So if you have a carboxyl group hooked onto an R group, you've converted that hydrophobic carbon hydrocarbon chain into something that's an acid. It now has those properties. Okay. Another functional group is called the amino group. This is a nitrogen containing group. It also has some hydrogens hooked to it. It is going to be polar because we have the nitrogen hooked to hydrogens on equal electronegativities. So it will give polar properties to whatever it's hooked to, and then it can also be a base because it has the ability to take up hydrogen ions out of solution. So where carboxyl functional groups can give acidic properties, amino groups can give alkaline or basic properties as well as being polar. All right, our next group is called a phosphate group. It's a pretty big one. It is a, sometimes it is, oops, I don't like that color. Let's do a dark blue. So a lot of times you might see it as PO4 because it's a phosphate with 4 oxygens. Sometimes it has a hydrogen, sometimes it doesn't. Because it can release hydrogens, a phosphate group can sometimes give a molecule acidic properties. We're going to see phosphate groups a lot in our cellular respiration, our cell communication, and our enzymes chapter. So whenever we talk about phosphate groups, just remember it's this big collection of a phosphate atom, 4 oxygens, and sometimes a couple hydrogens, depending on if it's ionized or not. And then our last functional group is called sulfhydryl. It's just basically a sulfur bonded to a hydrogen connected to some kind of carbon, some kind of R group. And because sulfur and hydrogen are not electronegative, this can give some polar properties to it. But what we're really going to be seeing these sulfhydryl groups in what we call disulfide bonds, where the 2 sulfur groups come in and actually bond to each other. They help give structural strength and integrity to proteins. So when you are reading about the proteins and learning about the protein macromolecules, they fold and twist and hook together. It is these sulfur-based bonds, these disulfide strong covalent bonds between the sulfurs that help to stabilize the internal structure of proteins. And when you do denaturing, when you mess up that 3-dimensional shape, a lot of times you're breaking these sulfur bonds. All right, so that finishes up this little mini lecture on carbons, bonding capacities, the versatility of it being in the backbone of all of our organic molecules, and then the role of these functional groups. When you add any of these functional groups onto a particular molecule, you will see those properties change for that molecule. So you'll see some of these functional groups in sugars. You'll see a lot of the hydroxyl groups in sugars. You'll see a lot of the hydroxyl groups in lipids. You'll see some aldehydes and ketones also in carbohydrates and lipids. You'll see the carboxyl group and the amino group in our proteins, in our amino acids. You'll see the phosphate groups and the nitrate groups also, or the amino groups, nitrogen groups in nucleic acids. So as you're building your knowledge of these organic molecules, we start with the carbon skeleton. We start adding these different functional groups, and then we get this diverse group of organic molecules. And so those topics you can read through the text, watch those other YouTube videos to learn more about carbohydrates, lipids, proteins, and nucleic acids. So if you have any questions, email them or come to a Zoom office hour, and I will see you next time.